Welcome to Exploring Science. So this week, you know, we're going to have fun exploring a couple of different realms of science. Our first presenter will be a graduate student in astronomy that will talk about exoplanets and how she studies them. And then, so Malena Rice will be our first presenter. And our second presenter is Josh Pondick. He's a graduate student in mechanical engineering and material science, and he'll be talking about 2D nanomaterials. So with that, I'm going to kind of hand over the baton to Malena.
Hi, everyone. My name is Malena Rice. I'm very excited to be here today talking to you all about what I think is probably like the coolest topic of all time, which is exoplanets. So I'm super excited to be telling you all about this particular kind of object in space. And so some of you may know what exoplanets are and some of you might not. I did not have any idea what an exoplanet was until a few years ago. So just to start out with definitions, an exoplanet is a noun, planet that orbits a star that is not the sun. So it is not a planet within the solar system. And so two of these three images that are shown here are actually objects in the solar system. And so they can't be exoplanets by this definition. So does anyone have a guess as to which of these is not an exoplanet? So A, B, or C, two of the three are not exoplanets. A here is not an exoplanet because this is actually Jupiter. And so Jupiter is a solar system planet. So it can't be an exoplanet because it's in the solar system. B is actually also in the solar system, and this is a little bit less well known, this image, but this is actually a picture of Pluto. And so Pluto is a dwarf planet, so it is also in the solar system, it orbits the sun, and so it can't be an exoplanet either. So C here is not something that exists in the solar system. We don't actually have very high resolution images of exoplanets, so we don't know exactly what they would look like, but this is sort of what we envision an exoplanet might look like. And so there are so many stars out there. There are 100 billion stars in the galaxy and 100 billion galaxies in the universe. So we would expect, if lots of stars have systems like the solar system, then planets should be everywhere. But the most nearby star is 4.2 light years away, which means that it takes 4.2 years for light to actually reach us from that star. And light's the fastest thing that can move in the entire universe. And so how do we actually study these planets if they're so far away? Well, there was this amazing telescope called Kepler that was launched in 2009, and that has been continually observing, trying to find these exoplanets. And when they launched Kepler, they had no idea how many exoplanets were out there. They didn't know what they would see. And it's actually been the telescope that has given us pretty much all that we know about exoplanets up to now. And so Kepler found thousands of planets. Again, they really didn't know whether we should expect lots of like solar system-like systems or if planets were common. But Kepler found some really, really incredible things that I'm really excited to share with you. So how did Kepler actually observe these stars? Because again, they're so far away. It's very difficult to learn about the characteristics of these planets that are so distant. Well, the way that Kepler found these planets was using something called transit photometry. And so in transit photometry, you continue to just stare at stars over time and watch for dips called transits in their brightness. And so if a planet passes in front of a star, a planet doesn't give off light, whereas a star does give off light. And so the planet blocks out a little bit of light as it moves across the star. You can kind of think of this as like public transit, something is moving across a street. And so the planet is moving across the star and causing this dip in the light. And so this transit photometry is a really powerful tool to look for these planets. And Kepler just stared at a bunch of different stars and saw lots and lots of these transits happening over time. So I want you all to take your fist and just hold it up at arm's length and just look at how much of the sky that covers up for you. And so that is actually the amount of the sky that Kepler was looking at. So it's just looking at this like tiny little fraction of the sky. And so that is what is shown on this screen here. And it found a huge number of planets just in that tiny little region. And so I'm going to play this video, and you can see time moving forward in the upper right corner. And there are lots of different planet transits that are being represented by these dots popping in and out within the Kepler field. And so you can see there are lots and lots of different planets of different sizes, different temperatures, and a crazy range of planets that we had never known existed before, from Earth-type temperature planets all the way up to planets that are so hot they have to be molten. And Kepler was really interesting because it also has this very strong observational bias. So in order to actually see these transit events, you need to have the planet pass in front of the star. But that's not going to happen for every single planet that exists. If the geometry of the system is tilted just a little bit, so if the planet's orbit is not in the exact right configuration, then you're just not going to see a signal. And so despite this fact, we still saw so many planets, which is really exciting. This has shown us that planets probably exist around almost every star in the universe. And so this also means that Kepler is really biased towards a very specific kind of system. And so this is a nice video that is showing you lots of different systems that were found by Kepler side by side with the solar system. So just to clarify, these systems are not actually spatially located in the solar system. They're just shown next to the solar system so you can understand what they look like to scale. And so the solar system planets are shown to the right, orbiting their sort of 4 rocky planets, and then you can see Jupiter and Saturn, and you actually can't see Uranus and Neptune here because they're too far out. And what do you notice as being different about the solar system planets versus the exoplanet systems? Does anyone see sort of a difference between all of these and the solar system? Also, yes, a solar system can have 2 stars. So there are some really cool planets that orbit 2 stars at the same time, which is crazy. Yeah, so what's totally unique about these systems is they are orbiting really close to their stars. And so they actually are really close in, because it's much more likely for them to pass in front of their star relative to our point of view if they are orbiting very close to the star. So what that means is we're seeing a ton of really hot planets that are right next to their stars. They're like much closer in than Mercury is to the sun. And so for just a couple of types of planets that we found that just we did not know to expect to see at all, I'm going to walk through some of the really cool types of planets that we've seen. And so the first here is hot Jupiters. Hot Jupiters are between 1/3 to 12 times the mass of Jupiter. And they're this type of planet that we found around a little bit less than 1% of all stars that are just zipping around their host star super fast. So one of these planets, it orbits its star within 2 and 10 Earth days. And the Earth, when it orbits the sun, it takes 365 days. So that's a year. So a year on these planets is between 2 and 10 Earth days. They're super fast, just whipping around their stars. And because of that, they're crazy hot. And so these planets have crazy atmospheres with like metal oxides, like vanadium oxide and titanium oxide, stuff that just doesn't exist on Earth because they're so hot. It's also always day on one side of these planets and always night on the other side. So when a planet is so close to its star, then it gets tidally locked, which means half of the planet always faces the star and the other half always faces away. This is actually the reason that we don't see half of the moon ever, because the moon is also tidally locked to the Earth. So we always just see one face of it. And so the dark side of the moon is the other side that we never actually see. So hot Jupiters are super cool, do not exist in the solar system, but appear to be fairly common elsewhere. And actually the most common type of planet that has been found in these extrasolar systems is super Earths. And these are between 2 and 10 times the mass of the Earth. So they're much bigger than Earth, but a little smaller than Neptune. And we don't have one of these in the solar system, but they're the most common planet that exists in other systems, which is interesting. It kind of makes you wonder if the solar system is like some weird anomaly and it's not like the normal system that you're used to seeing everywhere. And so these super Earths are really, they have potentially a pretty large range of properties. And so if they're too big, then they start to become similar to gas giants. So I can see some people are asking, are super Earths habitable? The smaller ones might be habitable. So if it's 1.6 times the radius of the Earth or smaller, then it is probably rocky. So it's like a rock that you can actually walk on. But if it's larger than that, then it's going to probably be a gas giant. So it doesn't really have a nice surface. There probably wouldn't be life there unless it's some sort of like microbial life that can float around in a gas giant atmosphere, which is not something we've ever seen before, but who knows? The universe always surprises us. And so these are super cool, but something else that's interesting about them is they're so massive that if you were on one of these super Earths, it would be really hard to actually get off of it. And so if you were on a super Earth that was 10 times the mass of the Earth, it would take 60,000 tons of fuel to actually launch a rocket off of the super Earth because its gravity is so strong because it's so massive. So if aliens existed on these super Earths, they might actually have a hard time with space travel. And so this is just a nice video of a super Earth similar to what we might expect the ones that Kepler found to look like. Just a reminder, Kepler found really, really hot planets. And so this one is probably just scorching hot and probably not very habitable. But that kind of brings us to the question of, are there Earth analogs out there? Have we actually found any of these? And are we alone? That's a big question in astronomy. And so this is actually a pretty old figure. This is as of 2015, some of the habitable zone planets that have been found. And so when I say habitable zone, I mean planets that are rocky, so they are not gas giants, you can walk on them, and they are just close enough to their star that liquid water can exist on the surface. So this is something called the Goldilocks zone, where they're not too hot, they're not too cold, and you can have water there, which we think is necessary for life. The problem is we actually don't know a lot more about these planets than their sizes. And that's because Kepler was just staring at this one little patch in the sky. So a lot of these stars are really far away, and it's really hard to get a strong signal and learn more about the planets. And so something really exciting that is coming up and to keep an eye out for is the data from the Transiting Exoplanet Survey satellite, TESS. So this was actually launched 2 years ago, and it's just starting to trickle in and find lots and lots of planets, and it's looking for all the nearest planets to the sun. And what's great about that is if you find nearby planets, then it's much easier to actually learn more about them. You can try to figure out what they're made of, and if they have like water on them, you can actually learn about their compositions and get much higher or much better signals so that you have a better sense of what those planets are actually like. And so this is just showing sort of the field of view of TESS. So it has 4 different cameras that you're going to see here, and it is actually going to scan pretty much the entire sky. So Kepler was just looking at this one little region, but TESS is just going to sort of sweep around, and it's actually finished taking most of this data, but it takes a little bit of time to actually reduce it and figure out what is in the data. So we expect that this should be finding thousands more exoplanets, which is super exciting. So here you can see, just for reference, the size of the Kepler field and the entire rest of the sky that TESS is going to be finding all these planets in. And Kepler also looked at a couple other regions in sort of an extended mission. So those are also shown here. And so towards the end of this video, you're also going to see something called the James Webb Space Telescope, which is going to be that's here. That's going to be launching in a couple of years. And this is actually going to give us spectra of those planets. So it'll tell us the compositions of those atmospheres, and we can actually learn more about whether they're hospitable for life. So I think that is all for my presentation. Thank you all for listening, and I'm excited to take any questions.
Okay, Malena, I can ask you a couple questions if that's okay.
Yeah, sure.
One big question we got is, if all of this information you're getting from Kepler, do you know what the Hubble telescope is doing? How is that different?
So the Hubble telescope is it's more targeted observation. So it has a very small field of view and it can only look at one star at a time. So if you've already found an exoplanet, then you can try to understand more about its properties using Hubble, but you can only look at one star at a time, whereas Kepler was looking at thousands.
Awesome. Okay, thanks. Another question would be, if you're on a super Earth and you're saying the gravity is really strong, does that mean that maybe the aliens that live on these wouldn't be able to jump?
Yeah, that's a good question. It would probably take a lot more energy to jump. So you could jump, but probably not as high. It would probably be a lot harder to jump on these planets.
Fantastic. Okay, just like, I guess one more question before we go into the breakout rooms. How do you name exoplanets? What are there rules for that? How does that work?
Yeah, there are some competitions where you can name some of the especially cool exoplanets, but usually there's a standard where they're named sort of based on their telescope. And so all the Kepler planets are like Kepler 1, Kepler 2, Kepler 3, and that just helps astronomers for organization. But if they're really, really cool systems, then sometimes they'll have like competitions where like anyone can try to name the planet and they pick the coolest name.
Awesome, thank you. We'll probably ask you a couple more questions afterwards for the follow-up video, but that was great, thank you.
Hi, so my name is Josh. I'm a third-year graduate student in mechanical engineering and materials science. And today I'm going to talk to you about playing with atomic Legos. So we're going to go from the scale of the universe all the way down to the scale of atoms for this talk. I'm going to talk to you more specifically about two-dimensional nanomaterials. And because I'm also a member of the Energy Sciences Institute, I'm going to tell you about their energy applications. So first, just a bit of brief background about myself. So I'm from Massachusetts, and I became interested in chemistry in high school. And I ended up going to Bowdoin College, where I studied German literature and chemistry. And I ended up doing research my senior year in chemistry. And I knew I wanted to pursue a career in research. Initially, though, I was interested in biochemistry. So I actually went to Boston, where I worked at Massachusetts General Hospital in a microbiology lab, which was really a rewarding experience. But I ultimately decided that my real true passions lie in the physical sciences. So now I'm here at Yale, and I study materials science. And you may not be familiar with materials science, and it's a field that sits at the intersection between chemistry, physics, and engineering. So just to kind of give you a sense of that, so in my lab, I have a background in chemistry, and so does another one of our postdocs. My advisor and 3 other graduate students in the group all have a physics background. And then we also have a postdoc and a grad student who are trained as engineers, and 2 postdocs and a graduate student who are trained as materials scientists. So you can see just within our group how interdisciplinary this field really is. And as materials scientists, we all seek to try to answer 2 main questions. The first is, what are a material's properties and what are the origins of those properties? So for example, let's consider 2 metals, iron and titanium. So both metals are very strong, but titanium is actually much lighter than iron. And in order to understand why that is, we actually have to look at how the individual atoms are arranged within these metals. So if we look at iron's atoms, they're arranged in this cubic packing structure. But titanium's atoms are arranged in this hexagonal packing structure. And it turns out that the difference in how the atoms are arranged, coupled with the weights of the atoms, gives titanium a much lower density than iron. And that makes it much lighter. So this is kind of the chemistry and physics aspects of material science. And the second question is more of an engineering focus. So now that we know what the properties of a material are, how can we use those properties for a practical purpose in the real world? So to continue with this example, iron is very cheap, it's abundant, and it's strong. And as a result, it's been used as a building material for transportation networks and for common household items for hundreds of years. Titanium, while being very attractive because it's both strong and lightweight, is quite a bit less abundant than iron, and therefore it's much more expensive. So it's really only used in certain niche applications like golf clubs, the aerospace industry, and also for surgical implants. So that's materials science in a nutshell. There's many different branches of materials science, and my specific branch deals with nanomaterials. So nanomaterials, very simply, are really, really small. If you consider a three-dimensional object, in order to be considered a nanomaterial, at least one of its length, width, or height needs to be on the scale of 1 to 100 nanometers. And the really cool thing about nanomaterials is they have different properties than their bulk counterparts. So for example, if I took a block of gold and I cut it in half, I would get two smaller blocks of gold with identical properties to the original block that I cut in half. And this will continue to happen as I keep cutting these blocks into smaller and smaller pieces. I'll just get a bunch of little pieces of gold with the same properties. But when I reach a scale of 100 nanometers, when they get really, really small, that ceases to hold. And the properties of the little particles of gold will actually change based on their shape and size, and they'll be different than the bulk counterparts. So you can see here, all these different sizes and shapes of gold nanoparticles will have different properties. And this can be really dramatic. So for example, these different vials are all filled with solutions of cadmium selenide nanoparticles. And when you shine UV light on them, they glow different colors just based on their size. So the smallest ones glow blue, and then as you increase their size, they actually get redder in color. And that's just by changing the size of the nanoparticle. There's no difference in the chemical composition. So that's just one example of how dramatic these property changes can be. Just to make sure that everyone's on the same page, because nanomaterials are really, really small and kind of hard to conceptualize. So a nanometer is a unit of length which is defined as 1 billionth of a meter. So if you break a meter into a billion parts, each of those parts is a nanometer. And I'm also going to talk a little bit about micrometers at some point. 1,000 nanometers are equal to 1 micrometer, which is a millionth of a meter. So does anyone have any guesses about exactly how thick our human hair would be? How many nanometers wide? I think 10 as a guess. 12, 50, 500, 1,000. Okay, so it's actually 100,000 nanometers wide, to kind of give you a sense of just exactly how small nanomaterials are. In fact, a virus is about 100 nanometers wide, and the actual width of the alpha helix of our DNA is only 2.5 nanometers wide. So nanomaterials are really, really small. So I study a kind of nanomaterial called two-dimensional materials. And these are layered materials. You can kind of think of them as like stacks of paper, where each layer is an individual sheet of paper, and then you can stack these sheets on top of one another. And these sheets are so thin that they're actually only between 1 to 5 atoms thick. So this is an image of 3 separate layers of a material called titanium carbide, and it's actually only 5 atoms thick. What these white dots are, these are actual images of individual titanium atoms. And it's difficult to see, but there are actually 2 layers of carbon atoms above and below the central titanium atom. So this material is actually 5 atoms thick. So they're extraordinarily thin materials. And you can think of each different layer of these materials as kind of like a Lego brick. So if we were to pull one of those materials out, layers out, and look at it from the top down, it would be kind of like a Lego brick, in that the atoms within the material are very strongly associated with each other. So it's very difficult to break that layer in half. And if we take the sheets and put them on top of each other, they'll stick together, just like you can stick 2 Lego bricks on top of one another. But because the layers are quite weakly associated with each other, they can actually be pulled apart, just like you can unstick 2 Lego bricks that have been stuck together. And just as a note, the reason they're called two-dimensional is that they're anywhere between 10,000 to 10 million times longer and wider than they are thick. So they're atomically thin, but a lot larger in their length and width. Now, as I mentioned, they can be a single atom thick. Graphene is probably the most well-known two-dimensional material. It's formed of carbon atoms bonded together in these sheets that are single atom thick. And if you take many thousands of these layers and stack them on top of each other, they actually make up a material which you can probably find in your classroom. I'm not sure if anyone has a guess, but I'll give you a hint. This material is used in a pencil. I wonder if anyone has any guesses about what material this would be. So I'm seeing lead, graphite. Yeah, that's exactly right. So the tip of your pencil is actually made of a material called graphite, which is the bulk version of graphene. So many hundreds of thousands of layers stacked on top of each other, and you get a material called graphite. So in addition to graphene, there's a large number of different kinds of two-dimensional materials that we can play around with. These include other single atom thick layers, some materials that are 3 atoms thick, and then others that are 5 atoms thick. And all 2D materials share this really interesting property that their properties are dependent on how many layers you have stacked on top of one another. So depending on the number of layers, we can change how they interact with electricity, how they interact with light, how strong and flexible they are, and even what kind of chemistry we can do with them. So for example, this is a material that I study. It's called molybdenum disulfide. It's formed from a molybdenum atom bonded in between 2 sulfur atoms. And it's so thin that a single layer of it is about 0.7 nanometers thick. And the monolayer of it, these are triangular single layer crystals of molybdenum sulfide that I grew. And you can see that they're purple in color. But I can change their color just based on their thickness. So this is an example of a bulk flake of molybdenum disulfide that's had one edge shaved off, as you can see schematically here. And as a result, we can see many different colors and a rainbow effect. And that's just coming from the different thicknesses of the flake. There's no chemical change. They're all the same material. It's just dependent on the number of layers you have stacked on top of one another, you get different colors. So those are cool properties, but 2D materials have a lot of attractive properties that are useful for many different applications, including electronics. This would be the brains of all the electronics that you use on a regular basis, including your cell phones or computers. They also have attractive properties for solar energy capture, making renewable fuels, and then even the batteries that run all of your phones, computers, you can use 2D materials in them. But no single 2D material is actually going to be perfect and do everything. They all have a number of drawbacks or negative features associated with them. And one thing we can do to try to mitigate those drawbacks or to try to make them better is to form what's called a heterostructure. So this is a really cool property of 2-dimensional materials. You can take 2 layers of different 2D materials and stack them on top of each other to form a new material called a heterostructure. You can kind of think of this as like stacking different colored Lego bricks on top of one another. And the cool thing about heterostructures is you can either combine the attractive properties of 2 separate materials, or you can actually get emergent properties. That is, properties that are different than just the properties of the individual layers that make them up. And here's an example of a heterostructure that I made in the lab. So we have a blue flake of molybdenum disulfide, maybe 5 to 6 layers thick, on top of 2 flakes of graphene, which are 6 to 7 layers thick. And what we do in our group is we try to actually use these heterostructures to make renewable fuels, specifically hydrogen. So hydrogen is a really attractive renewable fuel because we can make it by splitting water into oxygen and hydrogen gas. And we can do this just by hitting it with electricity. And it's a really attractive fuel source because when we burn hydrogen, it's actually the reverse of this reaction, and the only byproduct we get is water. So there's no CO2 produced at all. Now, one piece of this reaction is called the hydrogen evolution reaction, and that's what I study. So this reaction involves taking 4 protons and reacting them with 4 electrons to get hydrogen gas. And we need a catalyst to have this reaction to proceed, and molybdenum disulfide works as a catalyst. But you'll notice that this reaction requires electrons, which means electricity. So we need to get electricity into our catalyst in order to make hydrogen. And traditionally, you'd use a metal like gold to connect to our catalyst. But the problem is with gold and molybdenum disulfide, there's actually like an energy wall for electrons right at the interface between these 2 materials, which means that as we push energy into our system, all the energy goes towards pushing those electrons over that wall, and we don't make any hydrogen. And as a result, yeah, we see basically no produced hydrogen from modest inputs of energy. But what we did was we swapped the metal contact for a heterostructured contact. We used a material called tungsten telluride and made a heterostructure with it, with moly sulfide. And now there's no energy wall in between these 2 materials. So all the energy we put into the system goes straight towards making hydrogen, and we can make a lot more hydrogen than we could with a gold contact. So that's just one example of how we use heterostructures in our group to try to study energy. So we look at making renewable fuels, and we also study the chemistry behind lithium-ion batteries. So with that, I'd just like to thank, of course, our advisor, Judy Cha, who runs our group, the whole research team, and of course, our funding agencies that make the research possible. And I'm happy to take questions.
Thanks so much, Josh, for that wonderful talk. It's really cool to see, like, Malena's talk with, the solar system, and now we're getting to something really, really small, like down to the size of DNA. So it's really cool to see just the different sizes. So I have a couple questions here for you today.
Okay.
The first question is, how can the materials be 2D if you're making 3D things ultimately?
Yeah, so I mean, two-dimensional is kind of, it's a little bit of an exaggeration. They're called 2D because the length scales of their length and width are so much greater than their thickness that they are kind of like two-dimensional. Like I said, you can kind of think of them as pieces of paper where they're super, super thin, but they're much longer and wider than they are thick. So two-dimensional isn't an actual trying to describe their real properties. It's just it's kind of an easy sort of shortcut for sort of describing them.
I see. And on this topic of properties, you mentioned heterostructures and their types of properties. Is that similar to alloys and like the types of properties you get from mixing metals?
Yeah, I mean, it's a little bit different than alloys, because when you form an alloy, you're actually kind of combining you're actually sort of bonding the atoms together, so they're forming chemical compounds. In this case, the layers, you can still kind of think of them as being discrete. In other words, once you make the heterostructure, you can peel the layers off again if you wanted to. But it is similar in the way that the properties of the individual components, come together to form some sort of hybrid property, sort of like in an alloy. You can kind of get the properties of the two different materials. But as I mentioned, you can also get these emergent properties, that is stuff you would not expect just based on what each property of the individual layers are. You can get these sort of cool emergent properties.
I see. And I guess still on the topic of properties for our last question, thinking about like the types of atoms that you can use in these heterostructures, can you make electromagnets out of ferrous materials at that small of a thickness, or would the materials start to lose their property from being so small?
So that's a great question. Someone in my lab is actually starting to investigate potentially trying to make sort of ferromagnets using 2D materials. It really all depends on whether you can get a material that has a structure that is magnetic. There are certain compounds that can have magnetic properties. Another really cool and interesting way to induce magnetism in these materials is you can actually deposit chemicals, like molecules that have magnetic properties, on top of these layers. And because they're so thin, they can be heavily influenced by molecules sitting on top of them. So you can there's a couple materials that have some magnetic properties, but another really interesting way to do it is to actually put magnetic molecules onto the materials, and you can induce magnetic properties in them.
Right. Well, thanks so much for answering our questions, Josh. There are more questions that we have still to ask you, and those will be recorded in a video, which we'll send a link to you guys later on.
Great.
Hi, everyone. We're back with our presenters from this week, Josh and Malena. There are a few questions that were left unanswered from the presentation. So I'm going to start with Malena. Malena, thank you again for a great presentation on exoplanets. Some of the students had questions about planets in general. So how do you know if something is a planet? And if it was like a smaller body, could it be pulled into the orbit of the planets?
Yeah, so there are actually lots of asteroids that are also in the same orbits as planets. Like there are lots and lots that are actually in the exact same orbit as Jupiter, and they're just at a slightly different point in their orbits. They don't collide with Jupiter. And so what makes something a planet is that it has to be large enough that it is round. So it has to have enough self-gravity to make itself round, whereas these asteroids tend to be sort of bumpier. And it also needs to be big enough to sort of clear its orbit. So there can't really be a lot of other stuff in the orbit unless it is like dynamically interacting with the planet in a way that forces it to stay in that orbit. And so the planet really needs to be like the dominant gravitational presence in that space for it to be called a planet. So you also have asteroids that orbit the sun, but they're too small to be considered planets.
So going off of that, would it be possible for like a new planet to form in our current solar system or within the current solar system?
Yeah, that's a really good question. And we actually don't 100% know all of the details of how planets form, but it looks probably unlikely because we think that for planets to form, they need to be in sort of a big disk with a lot of gas. And so the early solar system, we think, used to have lots and lots of gas, lots and lots of gas in it, in addition to dust. And so that gas creates a drag force that kind of slows down all of these rocks and allows them to actually coagulate into a larger planet. Whereas right now, there isn't really a lot of gas in the solar system. It has cleared or it's become part of Jupiter. And so, because of that, if rocks get too close to each other, they tend to just crash into each other and become smaller instead of building up into bigger planets.
So could that explain why a lot of the large planets in our solar system are actually quite gaseous?
Yes, yeah. So the way that large planets form is if they reach a sort of critical limit within this disk where they're forming, they start to just have this like runaway accretion where just lots and lots of gas starts piling on once they've reached a certain mass. And so we have the small rocky planets, and we don't have any really big rocky planets because once they get to this limit, then they just start like piling on gas.
That's awesome. So along with the planets, you also spoke about super Earths. And so the students actually had quite a few questions about that. And one of the big ones is like, are they habitable? And has anyone ever explored like super Earths?
Yeah, so super Earths are a really exciting topic right now. They're kind of similar to Earth, we think, but they are bigger. And so they're actually easier to study because the planets have a stronger signal since they're bigger. We don't know yet if they're habitable, but we do have some spectra of some of the atmospheres of these planets. So that tells us a little bit about what their atmospheres are made of. Mostly we've just found out that the ones that we know of are pretty cloudy. So we don't actually know much about the surfaces. We just know, there are probably clouds on these planets. So that in itself is sort of interesting, but it blocks you from being able to see the surface because of the clouds. So it's really an open question right now. There are only a few of them that have been studied in any sort of detail. And so it's definitely a really big frontier moving forward where over the next 10 years, we might have a much better answer to that question than I can give right now.
That's awesome. So speaking of the clouds, if there are clouds surrounding the super Earths, what might the weather look like on those on super Earths?
Yeah, so these supers, it sort of depends. A lot of them that are really close to their stars, like a lot of the planets that I talked about in my talk, are going to be tidally locked. So that means half of the planet is facing the star all the time and the other half is facing away all the time. And so the two halves of the planet will have very different weather, where the half facing the star is always going to be really hot and the other half is always going to be really cold. And we don't really fully understand what that means for like the circulation of winds on those planets yet. And it really depends on like how thick their atmospheres are. So like we know Mars has winds as well, but it has a very thin atmosphere. And so whether or not there is a thick atmosphere will have a really strong impact on that weather. So there are really definitely a lot of unknowns, but we know some like vague things about these planets, and we also often think of planets being on circular orbits, but some of them get really close to their star at some points in their orbits, and then they get really far away. And so those ones are going to have really crazy weather where they heat up over a course of just a few days, then they're really cold for a really long time, then they heat up a bunch. And so because this has never happened in the solar system, we don't have a super good detailed sense of what that actually means, but it's an active field of study right now.
That's really cool. Thank you for answering these questions. It sounds like there's a lot left to explore, especially for students in the future that might be interested in your field of work or in astronomy in general.
Yeah, it's a really exciting field. So
Yeah.
I hope more people join us.
So Josh, there were some follow-up questions for your talk too that we didn't have time to get to during the session.
Okay.
So your talk was about 2D nanomaterials that you can kind of use like Legos sometimes. So first question that we had was, so is 1D just like a regular atom, a singular atom?
Yeah, so I mentioned in my talk that like two-dimensional is a way to talk about 2D materials. So nanomaterials are actually often classified as 3D, 2D, 1D, or 0D. So just to kind of clarify what those are. So I gave an example of just like a 3D cube, or which you can think of, and that's, I said that to be a nanomaterial, at least one of the length, width, or height had to be on the order of 100 nanometers or smaller to be considered a nanomaterial. So a 3D nanomaterial would be a three-dimensional object in which all of the sides are, the length, width, and height are all on that 100 nanometer scale. And generally, we would consider it as being sort of on the larger end of that scale to be three-dimensional, so maybe like 50 nanometers or more on all sides. So then two-dimensional, which is what I was talking about, is where only the thickness is on the nanoscale, whereas the length and width can be many, many times greater, even up to 10 million times larger than the thickness. So that's two-dimensional. You can kind of think of it like a sheet of paper as a macro scale analog to that. One-dimensional is actually where you have nanoscales on both the length and width, but then one dimension is long. So you can think of it like a wire. The example is a nanowire. So it's long in one dimension, but then in the other two dimensions, it's very small. And then finally, what's called zero-dimensional, another term for them, they're also called quantum dots, is when you have an extremely small three-dimensional nanomaterial in that its length, width, and height are all no more than, say, 10 or 20 nanometers. So you're really talking about only a collection of hundreds of atoms at most, and that's what's called kind of zero-dimensional. Once again, these are all just sort of shorthands for talking about different geometries, but they kind of get at sort of the shape of these materials.
Okay. Wow, that 0D is super small.
Yeah, the fluorescing nanoparticles I actually showed in the talk with the different colors, those are all quantum dots. So I think the largest one, maybe only 50 nanometers. Like they're all spheres effectively. So the diameter of the sphere is about 50 nanometers.
Cool. Some other questions. What is an alloy?
Right, so someone asked if a heterostructure is similar to an alloy. So an alloy is just, if you think of a metal, oftentimes we talk about, say pure titanium. So that would just be all of that chunk of metal is made up of titanium atoms. An alloy is actually when you take two different kinds of metals and mix them together to form a new metal that has kind of roughly properties similar to both of the ones that make it up. Some examples that you might be familiar with would be like brass or bronze are common alloys. Steel is also an alloy. So steel is actually iron that's had carbon infused into it, and that's what makes steel. And then stainless steel actually has chromium added to it, another element. So the chromium actually gives stainless steel its sort of corrosion resistant properties. So the different properties of the atoms that make it up will kind of add to make this new metal that has kind of an amalgamation of the properties of the others. And a heterostructure can be kind of thought as similarly. The chemistry and physics behind it is a little bit different, but it does have kind of properties of the two different pieces that make it up.
So for example, for an alloy, if you had one metal that was really strong and another one that was kind of flexible, if you mixed them, you could have one that was kind of strong and flexible.
Yeah, I'm not a metallurgist, so I'm not an expert on as far as physical properties of metals mixing. But I mean, like for example, as I said with the steel example, from a chemical standpoint, chromium is more resistant to corrosion than iron is, and the chromium effectively is like a sacrificial layer that gets corroded before the iron, which makes the stainless steel last longer than just say straight up iron.
Okay, cool. So you talked about using gold to input electrons into the system. Are there other metals that you can use for the same
Yeah,
kind
definitely.
of process?
Definitely. So, I mean, copper is kind of thought of as the common metal that's used in most electrical circuits on sort of a macro scale. It's because it's an exceptionally good conductor of electricity. We use gold in making these in our research because we can get very pure gold and it's very easy to deposit. So when we actually make and measure these two-dimensional materials, they're incredibly small, and we actually have to do something called nanofabrication, where we make incredibly small electrodes and devices to contact these materials. And gold just happens to be a particularly convenient metal to deposit, but we could use other metals. The issue is that the thing that I talked about with that wall, that energy wall for electrons to get over with molybdenum disulfide, that will happen with pretty much most metals. So it's not something that can be solved by just switching for a different kind of metal.
Awesome. And one final question. We had a bit of a controversy over, so when we talk about pencils, we talk about like pencil lead a lot, but you said it was graphite in pencils. I was wondering if you could clear that up a little bit.
Yeah, so I actually just Googled it. So just to clarify, so lead is not used in pencils. Lead is a toxic metal. The reason why pencil lead is called lead is apparently in Roman times, they actually used a writing stylus that was made out of lead. So the Romans liked using lead because while it's toxic, it's an incredibly soft metal, which makes it very easy to mold into whatever shape you want. So it was used quite extensively by the Romans. Unfortunately, they didn't realize that it was toxic, which we now know. So it's no longer used in most applications. Pencils, the tip of them now is graphite, which is at its heart just carbon. So carbon is a sort of non-toxic material to make pencil tips out of it. But the name lead kind of sticks around as a holdover from Roman times.
Cool. Well, thank you for clearing that up, and thank you for answering all of the questions and giving such an excellent talk today, both Josh and Malena. Thank you so much, and thank you for answering these questions, and we hope to have you guys back soon.
Thank you.
Thank you.